Hi, this is Radiation Across the Electromagnetic Spectrum, and I'm Kaylin Vasquez.
I'm Sophia Ukros.
And I'm Jenner Marcos.
So we started off with ionization smoke detectors, and this is nuclear reaction. At the top here, you can see the front and back of the one at my house. And the way this works is that a tiny portion of radioactive material called americium 241. It ionizes the air to create a steady current between two charged plates. When smoke enters the chamber, it sets off the alarm. So the type of nuclear reaction involved is the decay, and it emits alpha particles. You can see it right here. This is the alpha particle it emits, and the typical activity is 11,000 decays per second. Energy emitted from the particle, each particle has about 5.5 mega electrovolts. The radiation is detected indirectly because alpha particles collide with air molecules. The collisions ionize the air and create positive and free electrons. Two charged plates attract these ions. They establish a small constant electrical current. When the smoke enters, fewer ions reach the electrodes and particles attached to the ions, slowing down the current and setting off the alarm. The radiation is safe in this application because alpha particles have low penetration power and the radioactive source is extremely small and sealed inside of the detector. No radiation escapes the chamber because of a low penetration power, and under normal use, it can be held as a household appliance. Holding the detector has no measurable health risk, and the exposure is far less than natural background radiation. So, moving on to my hand-drawn sketch. Here you can see the radioactive source within the smoke detector. And then here is the ionization of air. You can see the radioactive source emitting alpha particles, and the electrical current is very high. So here the current detector is not detecting a slow a slow current, so the alarm is not being sound here. But here you can see the smoke enter and it's disrupting the current. Therefore, the detector picks it up and alarms the sound. So, microscopic radiation process. Americium undergoes radioactive decay emitting high energy alpha particles. Through the process of ionization, the alpha particles collide with N and O particles in the sensing chamber, breaking them apart to create positive ions and free electrons at an atomic level. Another microscopic process is the current generation and the interactions of the smoke particles with the ions and electrons. And the macroscopic radiation is the results, the circuit detection, because you can see the circuit up here at the top, the trigger, and the alarm sound, because obviously you can hear it when the current is disrupted.
This is our part two of the radiations. I did UV lamps and document authentication. Um, UV light reveals security features in documents, but why does it do this? Ultraviolet light is used to reveal security features because these features are difficult to replicate or counterfeit. Government documents such as driver's licenses and passports contain special inks and materials that do not respond to visible light but fluorescence under UV light, allowing authenticity to be verified while keeping the features hidden during normal use. As shown here in the experiment, it shows that on the the professional ID, there's fluorescent lighting here, while on the school ID, there's no fluorescent lighting here. For the identity of ultraviolet radiation, its full name is ultraviolet electromagnetic radiation, and the radiation wavelength range is in UVA and ranges between 315 to 400 nanometers. Commonly, the lamps are 365 nanometers. Energy per photon is equal to 3 to 5 EV per photon, and the typical power output is a handheld UV light, which is commonly used to inspect any legal documents. And this is usually between 1 to 10 watts of electrical power, assuming that most lamps are 365 nanometers. Um, the UV radiation generated in the lamp is made by electrical energy getting excited inside of the lamp as the electrons return to lower energy states once they come off the fluorescence. They release energy in the form of ultraviolet photons, producing UV light at specific wavelengths. Fluorescence is what occurs when a material absorbs a high amount of energy UV photons and re-emits that lower energy photon in a visible range that is visible to the human eye. Special inks and fibers or coatings in special documents are designed for fluorescence to be revealed, which showing the hidden patterns or markings only when exposed to UV light. As shown in the diagram, it shows the UV lamp, which is giving off the UV radiation in the form, it's invisible to the human eye, but gives off the purplish hue. And the part of the ID that is fluorescent, it absorbs that radiation and it takes it and it puts off instead a lower photon energy, which is visible to the eye now. Um, in the diagram, it shows how the fluorescent comes off of the lamp in a not comes off of the lamp in a non-visible light, radiating off high energy photons that are too small for the human eye to see. The area of the ID absorbs that energy and comes off as fluorescent and absorbing the energy and re-emitting it off of a lower energy. This is now shown as visible light or fluorescence, which is used in the important documents since it is only visible when using a UV lamp or for security reasons. This form of radiation is non-ionizing because it is not harmful to humans.
This is our third and final part of our homework assignment, which covers microwave ovens. The observational focus of this part was to connect radiation to energy transfer, which will be explained further in the explanation of a microwave oven. So, what type of radiation do microwave ovens give off? Well, based on the name, it emits microwaves, which are a form of electromagnetic radiation. This radiation is non-ionizing, meaning the photons do not carry enough energy to remove electrons from atoms or molecules. Because of this, microwaves cannot damage DNA, nor can they make food that are placed inside of it radioactive. This is very different from ionizing radiation, such as X-rays or gamma rays. Instead of changing the structure of atoms, microwaves mainly cause molecules to move. This distinction is important because it explains why microwaves are safe for everyday use while still being effective at heating food. Most microwave ovens operate at a frequency of 2.5 gigahertz, which corresponds to a wavelength of about 12.2 centimeters. The energy of a single photon depends on the frequency of the radiation, according to the equation E equals H times V. Because microwaves have a relatively low frequency compared to visible light or X-rays, each microwave photon has a very low energy, about 1.2 micro electron volts. This this low photon energy explains why microwaves cannot cause chemical or nuclear damage. Instead, their effect comes from how many photons are delivered, not how energetic each individual photon is. So how is radiation generated in a microwave oven? Inside of a microwave oven, radiation is generated by a device called a magnetron, which you can see from the first diagram. You should go up one. Uh, the magnetron converts electrical energy into high frequency electromagnetic waves. It does this by accelerating electrons using electric and magnetic fields. As the electrons move, they pass through resonant cavities inside the magnetron, which uh, causes them to oscillate and produce microwave radiation. These microwaves are then directed into the cooking chamber. Once inside the chamber, the waves reflect off the metal walls and form standing waves, which can be seen in the second diagram, which creates regions of higher and lower microwave intensity. This is why food sometimes heats unevenly if it is not rotated properly. So how and why is food heated once it's placed inside a microwave oven? Microwaves heat food mainly by interacting with polar molecules or water molecules found on food. Water molecules have a positive and a negative end, which allows them to respond to the oscillating electric field of the microwave radiation. As the electric field changes direction billions of times per second, the water molecules continuously rotate to realign themselves. The rotational motion increases the kinetic energy of the molecules. When these molecules collide with neighboring molecules, that kinetic energy is converted into thermal energy or heat. Food with higher water content absorbs microwave energy more efficiently, which is why moist foods generally heat faster than dry foods. There's an important difference between photon energy and total power. Photon energy refers to the energy of a single photon and depends only on frequency. High frequency radiation like gamma rays has a very high photon energy, while microwaves have very low photon energy. Total power, on the other hand, refers to the rate at which energy is delivered, measured in watts. Power depends on both the energy per photon and the number of photons emitted per second. Microwave ovens typically operate between 600 and 1200 watts, meaning an enormous number around to 10 to the 26th to 10 to the 27th power photons per second are delivered to the food. Even though each photon is low energy, the large number of photons results in in significant energy transfer and effective heating. So what does this mean in terms of the electromagnetic spectrum? This means that there is ionizing radiation, which is high energy and more harmful to humans. On the other hand, there's non-ionizing radiation, which is low energy and it does not harm humans.
I got ionization smoke detectors, and what that means is that it was the highest energy out of all of them because it had the highest frequency, yet it was contained, so it was not damaging humans in the way that it could have if it weren't contained.
I got the second highest energy out of our radiations that we did. I did ultraviolet, which is on the edge of non-ionizing and ionizing because it's not directly harmful to humans in that way.
And I had the microwave oven, which is one of the weaker types of radiation, being more towards the edge of the electromagnetic spectrum. Without going too much into it, people can honestly tell that it's the least harmful as we use it in our everyday lives. And if it was harmful, then we wouldn't really be using it.
Thank you.
Thank you.
Thank you.